Well, we'll see if this comes on. All right, well, let's talk about it and we'll kind of get going here. I think grades overall in the class are like really high. I think it's above a 90 at this point for the average. So, you know, these exam scores will always be a little bit lower than what you're doing. Hopefully, like the assignments, like especially for you guys, you're all, I mean, getting almost all the points on assignments and showing up. So that part shouldn't be an issue kind of with your grade. Am I echoing now? That's so weird that I can't hear it up here. So yeah, grades are kind of in a good place right now. We've got one more exam. If you didn't do too well on either this exam or the other one, you go back to the syllabus. Remember the weighting kind of changes. So come on, fingers crossed. See if we can get to work this time. So you guys can, there we go. I just need to not go in presenter mode. So I've identified your kind of highest and lowest, and notice they're weighted a little bit differently. If you look at the syllabus, your lowest exam is as low as 12.5. So if you do better on the final than you did on either one of these, you know, it decreases how much it's going to influence your grade. And if you do better on the final, that grade influences your grade a lot more than the other ones. So there's still room for kind of making up for not a great exam. The final is going to be very different. So it's not cumulative and it's less computational. Right? I want to dive into regression a lot more with you guys and some other topics that I don't go as extensively with my other sections, but I think it's really useful. But it's a lot more like interpreting statistics as opposed to like computing. I need to go through, I think I have all the iClickers in, but I need to go through this last month and any kind of excused absences I haven't built in yet. There should be a handful, so I'm still going to have a folder with all the emails and things for excused absences. I still need to go back through. I also know that I graded that second individual assignment and then realized there's no scores in there. So I don't know why those didn't save when I was going through them. But hopefully I should be able to get that done early next week. And then once I have those in, everything should be kind of up to date there. I got the other Excels are graded. So we should be pretty up to date. Okay. Any questions for me? Hey, you guys should have said something. I remember going through them. I don't know why none of the grades are up there anymore. So this is very frustrating. But if there's no questions for me, I posted the lecture slides. It'll be for next week, but we'll kind of start on them today. Okay. So, you know, we were looking at two population examples, and we're looking at the difference in sample means. So what we'll talk about today is something a little bit different, which is we're going to have the same sample, but we're measuring that same set of subjects at two different times, right? So it doesn't just have to be time related, but primarily the examples I'll show you will be time related, and that's where we see match pairs used the most, right? So, you know, an example might be something like, let me make sure I hit record here. Okay, I did. Might be something like I rearranged, you know, the workstations and I measure productivity of my 10 workers before and after. But it's the same 10 workers, right? Or maybe I'm looking at you guys and I say, okay, what was the difference between your performance on exam 1 and exam 2, right? So I'd have two samples, but it's the same set of people, okay? So instead of calculating sample means and then taking the difference, what I'm going to do is take the difference in the actual variable. So I would have something like this. I would have, you know, I don't know. This is Joe, Mary, etc. Right? I would have their before and I would have their after productivity measures. Right? So I don't know, 20, 15, 12, 13, etc. What I'm going to then do is just find that difference in productivity for every worker. So this person, productivity fell by 5 units. This person, it went up by 1, so on and so forth. Once I have the difference calculated for every individual, I'm then going to find the mean of that difference variable, right? Or what we'll kind of call our mean difference, which in this example would reflect the average change in productivity. Right? So I kind of, instead of calculating the average before and average after, I'm able to break down how much each individual's productivity changed and then find the average productivity change kind of across those workers. So it's a slightly different than what we were doing before, but it actually makes life a lot easier. So kind of revisit, right? Oops. Confidence intervals, right? So basically when I'm doing these mean differences, it's exactly like I've got a sample mean, but only a sample variance. So I use that student t-distribution because I only have a sample variance, and my degrees of freedom goes back to n-1. So, you know, these examples really look no different than what we were doing with one population sample mean, sample variance examples, other than we had that added step where we had to create this difference variable. And then we're just finding the mean difference, the variance of this difference variable, the sample size, and, you know, kind of relating this to what we had before. It's going to look almost identical, a little bit difference in notation, just to signify that, look, we calculated this difference variable, kind of used two other variables to find this difference variable. But other than that, we really treat it the exact same. So there's not really a whole lot new here. Any questions on this before we keep moving? Like I said, not anything wildly different. So we go to kind of this first example, right? Let's say like we had those 10 workers, we calculate the difference and find an average difference of 8.5, a variance of 121, and I want to build a 95% confidence interval. Well, at the 95% confidence level, my alpha would be 0.05. I've got alpha over 2 on each side of my confidence interval. So 0.025 is the area that I want on each side of my confidence interval. And then my degrees of freedom is simply n-1. I said I had 10 workers, so my degrees of freedom would be 9. We go to that t-table. We wanted 0.025 on each side of the confidence interval at degrees of freedom of 9. 2.262 would be the t-value, or the number of standard deviations away I need to go to build that lower and upper bound, right? So I plug that t-value in, and that's just a matter of plugging in those values that I was given. So not really no different, other than we have to create that difference variable before we find the average of or find the mean of it. So, you know, in this example, if this was my confidence interval with 95% confidence, what could I say? So remember, we were measuring before and after productivity of some workstation change. So with 95% confidence, I could say that changing the workstations led to not just a difference, but yes, an increase in productivity, an average increase in productivity across my workers. And the reason why this is a little bit more valuable than what we were doing before, let's say I use two different companies. I'd be comparing like the average across one set of workers to the average across another set. Here, what I'm saying is the average change like per worker, right? Like I've controlled for a lot because I'm measuring the productivity of the same person before and after. So I'm controlling for anything else that might impact productivity. If I take two completely different samples, well, maybe sample one has a slightly higher education level. Maybe they have, you know, slightly, I don't know, all the other factors that might matter. But if I can measure the difference between the before and after within each individual, well, I can kind of control for a lot of those things. So this is going to be our first step and look at thinking about how do I control for other factors that are going to be influencing the variable I'm interested in, right? This is like the first snapshot of it. Okay. So we can also do hypothesis testing, right? We've got the same three tests. It's just now I've got this assumed true kind of average difference. Right? I think primarily in the examples I give you here, just like with our two population, I'll use the assumed true value of 0 here. Because what that's really saying is is the average difference above zero, or has it increased? Is the average change, or the average difference below zero? Did it decrease? And is the average difference anything other than zero? Was there a change, right? Did we see any evidence of a difference at all? So same three type of tests that we had before. Once again, this test statistic, it really looks just like the one population test statistic we had when we had a sample mean and a sample variance. It's just we use different notation to identify, yeah, but this is a sample mean of a variable we created from two other variables, right? This difference variable that we created. From there, all the same principles would apply that we were doing with hypothesis testing. Oh, did I get these out of, there we go. So let's say we had that same sort of example. I could find my test statistic, right? I'm using that zero there. Just did productivity increase or did it change, right? So is it anything other than zero or anything above zero? And then it's just a matter of kind of plugging in the other statistics I was given, my sample mean difference, my sample variance of that difference, and my sample size. So nothing really, not reinventing the wheel here. So I'm going through it kind of quick. But let's say we wanted to do another kind of confidence interval, kind of put some actual values to this and think through what we would do here. So let's say I've got, I think just hearing more examples too of this matched pairs makes it make a little more sense. And shows like the power of what we could do with it. So let's say a nutritionist wants to determine whether or not calories have decreased after they posted the kind of calorie content on the menus, right? This was like a big change. I feel like this has probably been about 10 years ago now when you started to see this pop up and like everywhere. So you've got 40 Starbucks card holders, right? So you've got the same 40 people and you can see what they were purchasing before and after this change. So you could determine calorie consumption before and after, right? Did posting this have any influence at all? You find the average change is 2.1. So not a very strong, there was no strong evidence that calories are changing a lot, but you did at least see that it looks like they actually went up, right? You find a sample difference, right, of 64, and you want to build a 99% confidence interval. So 99% confidence interval, the alpha is 0.01. I want half of alpha on each side of my interval, so 0.005. My degrees of freedom in this example would be, goes back to n minus 1. So 40 minus 1 is 39. We would go 0.005, 39 degrees of freedom, 2.708, right? Now that I've got that number of standard deviations the way I need to go, right? I'll plug that in, plug in my sample variance, sample size, that kind of sample mean difference there. And really, it's a matter of computation at this point. And then this is one of my favorite memes. I can't reveal them in slow-mo now, but if any of you haven't seen Napoleon Dynamite, you should all go watch it. This came out, I believe it was 2005, would have been right before my senior year started. And I thought it was the funniest movie ever. I still think it's hilarious, but anyways. So also have to give credit to Eli on this next one. When you think it's over, the confidence interval strikes back. So he sent me an email and that was the title. And I just thought it was, I thought it was great. Right? So, we can do these confidence intervals for matched pairs and it really looks like just like what we were doing before, right? We can also do some hypothesis testing. So let's work through kind of this Starbucks card holder one. Think about how we could do some hypothesis testing. I should have just gotten rid of this from the slide, but I guess we already know ahead of time, right? But the original question was, have calories decreased, right? Well, if we're thinking about have they decreased, what we're thinking about is that difference. Remember, when we're calculating this difference, this is like, could be before and after calorie consumption. So we got different Starbucks card holders. The only way that it's decreased is if the after minus before is less than 0. Well, that's what we were doing when we calculated that difference variable, right? We took the after minus the before. So if I want to know if something is decreased, I'm assuming that I'm trying to find if that difference is less than 0. So I assume the opposite is true, which is that it's greater than or equal to 0. So my alternative hypothesis here was that that difference is less than 0, which means my null, I assume it's greater than or equal to. Okay. Now, I think here in the slides, I probably changed it, or I forgot the negative sign before. Oh, I guess I didn't, right? So this one is going to be one where we actually already know our rejection decision, right? If I've got a left-tailed test here, only evidence that goes against the null and supports the alternative will be evidence on the left side of the distribution, right? But I actually found something that's to the right of my assumed true difference, right? So what I'm thinking about here is I've got the distribution of these sample differences. If what I assume to be true is in fact true, they'll be centered around 0. Okay? Well, the problem is if I see 2.1 here, and I had a left-tailed test, well, right away, if I wanted to use the critical value approach to remind myself of this, my critical values are going to be on the left-hand side, which my student t distribution is centered around 0. So my critical value should be for a left-tailed test. All my critical values for a left-tailed test will always be negative, right? Well, if I saw something that was above the assumed true value, I know that I'm going to have a test statistic that's positive. There's no way it's going to be in my rejection region, right? Now, I could go through this and prove this to myself, right? I could look up these critical values. So if we wanted to do that, we said the degrees of freedom was 39. So 39, if I have a left-tailed test, it would be negative 1.304. So let's pop this up so I can write these down here. So we would have 39. So negative 1.304, negative 0.05 would be what? Negative 1.685. And I'll blow this up in a second. And negative 2.426. Okay. So I could find those critical values. Now I could calculate my test statistic. We said that's just going to be take that sample difference, subtract the assumed true difference. I really don't have to do this step if I'm using 0. And then divide by, now really what we're dividing by is the standard deviation of my sample differences. But that's just going to be the variance I find from that difference variable divided by my sample size, right? So this was, I already forgot, I think this was 64, and I think this was 40. But we're going to have a positive test statistic. It's not going to be anywhere in that rejection region, right? Now, what if I wanted to find the p-value here? It's a left-tailed test. It's kind of a weird one. I won't ask you one like this in the exam, like confuse you, right? It would actually be the area to the left of whatever test statistic I find here. So my p-value is definitely going to be above what value? The area to the left of 0 would be 0.5. So my p-value is going to be greater than 0.5. If I only reject when the p-value is less than alpha, let's just say assume my p-value for now is 0.6, it's not going to be less than any of my three benchmark alpha values. So I'm going to fail to reject massively. But that makes sense. I found evidence, right? A positive value, which would actually support the null, right? So I could go through this. I think if I plug those values in, I got 1.66. Like I said, nowhere near our rejection region. Now, once again, if I wanted to find the p-value for the student t, unless I do it in Excel, I'm going to be limited using that student t table, because if I go to 39, I can't find 1.66. I'm going to be in between two values here. So one thing I'll mention on the exam, I graded it very leniently. When I asked you for the p-value, I looked at the wrong row when I gave you the numbers, thinking you could find exactly your test statistic. It was actually off by like, I think 2 degrees of freedom. But a lot of you kind of said, it's going to be approximately 0.025 or anything kind of, you use the Z table to get a good idea. I kind of counted it as correct. But yeah, so unless I give you exactly a value that you could find here, 1.66, yeah, I guess the p-value is going to be close to 0.05, but I can't tell you exactly what it's going to be, right? But with Excel, we could. Right? And so I'll play around here today in a little bit in a file. It's on Excel. I think is pretty interesting. I was actually kind of surprised by the results. So any questions over any of this before we keep moving here? Is this making sense? This shouldn't be too bad. So I originally had this one where we were looking for differences in male and female suicides. I don't know. I wanted to look up something different. So I went out and grabbed a bunch of COVID data. Let me see. So if we go to files, I moved all the old data, I think, and I only have 2 files up under, well, they're all in this old data folder, but only 2 once you first click on the in-class data. So this isn't completed, but I'll kind of walk through some examples of matched pairs using some county level data. Okay. Download, open. And I had the complete version up there, but I only kind of worked through and explain exactly what we're doing and think about maybe some differences. So if some things change, how would I alter my approach? So got all these tabs. I went out to the CDC and pulled COVID cases. Actually, it came in, it was like by day, or reported by day in each county. And so I had the total number of cases and the total number of deaths. Now the problem is, this is some I'll teach you a little bit about data cleaning and collection. Notice all of these are always getting larger. So the data comes in as the total number of cases since like the beginning of COVID tracking, right? So notice, like, I think this is, I forget what state this is, but right, there's some small, like it might be Alabama, and you've got a small rural county where even back in March and February, they at least probably the zeros here probably mean they just hadn't start tracking yet. All right, they didn't have any kind of confirmed cases. So really, these earlier months probably aren't as reliable. As we get more kind of further into this, right, we probably get a little bit more reliable values. But this is the total number of cases and then the total number of COVID deaths. So here it makes a lot more sense, right, especially in these early ones, like we have a lot more zeros here for a lot of counties. So I kind of moved this. So if I had September and October, the difference between the two would be the number of added deaths, right? So I look at the total number of deaths ever in October versus September. The difference there would be how many were added that month. Right? So I did some of this. So let's first look at cases. I think I must have, yeah, here we go. So I've got, so we can see this, right? What did I do here? You can see all the headings. So I have the number of new cases that were added in October 2020 and the number of new cases added in 2021. So my initial thought was, can we say anything about, relative to last year, have the number of cases gone up? Have the number of deaths gone up? And kind of those types of questions. So what I first did was convert those into then kind of averaging this out, dividing it by the population. So across all these counties, I don't have their names, but there's like this FIPS is like a county level identifying number that the government uses. So I counted for population and then said, okay, what was the difference between this October and last October? Now, just off the face, you'll notice these are a lot of positive values, right? In fact, I don't know, we got to scroll down a ways. There's a negative one, right? So there are some counties where cases are lower this October than they were previously, right? But I don't want to look across every single county, right? Now, what I then did, so I took the difference, right? I created this new difference variable. So in practice, you wouldn't have this already. Well, all I'm doing there is just take this cell divided by this cell, right? So I can actually delete this. If I have the number of cases in 2021 in October, per person or divided by the population, and I had the same thing in 2020, to find that difference, kind of my before and after, I would take 2021 October cases minus 2020 October cases. If I then get this big black plus sign, double left click, it fills it in for every single observation. Okay, it's a nice little shortcut. So here, I'm going to find the mean of my difference variable, just using my average function. Right? It's easy enough. Control Shift, Command Shift to select the entire column. var.s, so I'm finding the variance of this difference variable. That's easy enough. And then I'm going to use that count function to find the sample size, right? These are all things that we've done before. It's just now we're doing it for this difference variable, okay? Make this a little bit larger here, sorry. So let's say I want to do a right tail test. I want to determine, I want to test for have cases gone up, relative to last year. Okay? So my test statistic would be, well, just take what I have here and leave it up here. Take my sample difference, right? My mean difference. Now my assumed true difference here, if I just want to know, is it greater, has it increased? Is it greater than 0? I could subtract 0 here, but there's no need to, right? Subtracting 0 doesn't change anything. But I'll do it just to kind of show you something here in a little bit. I then divide that by the square root of whatever that variance I found in the difference variable was, divided by my sample size. Okay. So I can come up with my test statistic just using Excel as a calculator. Right? There's no built-in, unfortunately, there's no built-in thing there. Actually, there might be, but I'll show that to you in a second. We could just do this way, and there's some value to doing it this way, which I'll try to highlight. Okay. So we have a wild test statistic here, right? I mean, we have a huge sample size, so that makes sense. So for our p-value, right, we're going to use the student t distribution. Here's my test statistic, comma, sample size -1 is my degrees of freedom. And then remember, in Excel, kind of comma 1, it finds the area to the left of that test statistic. But if I have a right-tailed test, I actually want the area to the right, which means I need to do what? Yeah, subtract it from 1. And I basically have a p-value of 0. So with like any level of confidence, I can actually reject, right? If I had a right-tailed test, what I was saying was the alternative was that this difference was, greater than 0, which meant the null was that the difference was less than or equal to 0. Right? So with any level of confidence, I can reject that cases have went down, right? Across all counties. The average change across counties was negative, right? That it's went down. Which I was a little surprised at, but maybe this is because I don't know. I felt like last year it was kind of maybe it seemed more real, I guess. But anyways, so we've got this right-tailed test. We can clearly reject our null hypothesis. What did I want? Oh, so here's another way that you can find that p-value. Okay. So there's a built-in thing called t-dot test. Right? So what you can do is use this t-dot test. First, select the variable that you want to kind of like to be your after time period, right? Here, this is 2021. So I'll select that, comma, this is where I have to go all the way, scroll back up to kind of show you this. The second array, well, this was my second variable, was the cases in 2020. Control Shift, I selected that entire column. And then comma, what type of tailed test do I have? Well, here I have a right-tailed test, so that would be a one-tailed test, comma, we have 3 different options. So I didn't show you how we do hypothesis testing with 2 populations, I don't think. It's really the same as how we did it with 1. It's just that there's more moving parts, so it's nothing new. There's really nothing new to show there. Other than you can start to use this t-dot test to kind of skip all the steps. So if I use this t-dot test, what it'll do, I'm doing a matched pairs example. So comma 1. If I had like a sample mean with only sample variance example, I could actually use this option 3. So instead of calculating the sample means, the sample variances, plugging everything into my test statistic equation, Excel will do all that for me. It will also do all of that for a matched pairs example. So what it's going to do is it's going to use these 2 variables. Behind the scenes, it's going to create this difference variable. It's then going to find the average of that difference variable, the variance of that difference variable. It's going to plug everything into a test statistical equation that's pre-programmed. It's then going to look that up from a student t distribution at the degrees of freedom of n-1 and spit back out at you the p-value. So it's going to do all these steps, right? Even creating that difference variable, but just behind the scenes. So hopefully, well, here they both look like they're 0. It's probably a little bit more difficult to see unless we had something that actually had some numbers here, but they will basically give you the exact same p-value, right? So doing all the steps yourself, ending here with that t.dist, t.test will do all that's behind the scenes. Right? So it's kind of a nice tool. So the problem with this, and yeah. So over here, right, if I wanted to test for whether or not COVID cases have increased, that average difference is positive, I'll assume the opposite is true. So I'll assume that across counties, on average, cases have declined, right, or are less than or equal to 0. I found strong evidence against that, so I can reject that null hypothesis. I found strong evidence that actually supported the idea that cases have went up. So one of the problems with the t.test, the built-in, is that the only value it can test against is 0. So let's instead say, okay, I found pretty strong evidence that cases have went up. So the cases, per person, can I say that they are greater than, I don't know, 0.005, all right? So basically this is like what, 0.5%. Every month is less than 0.5% of people, or has the change been 0.5%. So instead of using that assumed true difference of 0, now I'm saying not only have cases increased, have they increased by more than 0.005, all right, 0.5% of the population. Well, there I get a little bit more of a reasonable statistic. I'm going to try to get one so that I can show you that. Notice the p-value changes here. For that t.test, the only value it can test against is the assumed true difference of 0. So it's nice, does a lot of the work behind the scenes for us, but we can't test against anything other than 0. I don't know why they don't just add in like a fifth option there where you can like tell it the assumed true difference and then it would work fine. But once again, I don't write the Excel formulas, so, or program the Excel functions. Yeah.
So not scenario, would the hypothesis change to 7?
Yep. So really what we were doing there in the test statistic, this is what we wanted. And now notice, we've got such a high sample size that like, I barely found evidence that goes against this, but with a high enough sample size, I can actually still reject that. Well, actually, sorry, I can't quite reject it at the 95 and 99% levels, but I could reject it at the 90% level here still. Any other questions on this? Yeah.
So why would you not just directly find the standard deviation or the sample standard deviation?
So remember, what's in this denominator? It's a little bit different. So this is the standard deviation of my mean differences. This is the variance that just exists in that difference variable. So how do I want to say this? It was kind of like before when we just had some variable X. We then took a sample and we thought about the distribution of my sample means. Here we've got data that just gives me the difference variable, right? It just gives me X. If I then think about taking a sample mean from that sample mean difference will have its own distribution. So to determine the standard deviation of those mean differences, we have to use the variance that existed in that original difference variable. You could, but then this would have to change, right? This would be Yep. Does that make sense?
Yeah.
I don't know why I just always do things in terms of the variance. I think it's just because that way this is a standard deviation, but it's of a standard deviation of your sample difference and not just the difference variable itself. So maybe keeping those separate. That's usually why I do that. Just any other questions there? Okay. So we'll skip. Oops. We'll skip the depth one. This also is this was an awkward title, depth test class. But I thought something that was more interesting results, because I did take a look at this ahead of time, and we can just build it the exact same way, is I also found kind of, I had the cases and the deaths, right? So maybe the question is, has the percent of people dying who have contracted COVID, has it changed, right? I could do as it went up or down, but I just want to know, is it any different? Like, because honestly, I mean, I'm really surprised with these results, because well, we'll see it why. Because really what we're saying is, has it changed? What would you think has probably happened? Relative to October of last year, we didn't have any vaccines, right? So you would expect wildly different death percentages if the vaccine is preventing people from not only getting it, but from getting extreme cases, right? Like, that's one of the things I've heard a lot. And I'm not saying anything about vaccine here, but this is just like this, the narrative, right? That you would, this is why we would look at the data. So we took the difference. So sorry, actually, before I get here, all I did was take the number of new deaths divided by the number of new cases in each county. I then said, okay, here's my 2021 kind of death percent from COVID. So what? In this county, about 3% of people who got COVID died. And this is pretty high, actually. This one was in 2020 was about 1%, right? So in this county, it looks like there has been a difference. Right? Actually, people were more likely to die from COVID in that county. Now, there's a myriad of other factors, right, that we would want to build in here, but this is just kind of starting. So I took the difference between 2021 and 2020. We could find the mean of that difference variable pretty quick. We could find the variance of that difference variable pretty quick, and we could get our sample size, although it's going to be the exact same as the number of counties we had before, because every county has to report here. And then I'm going to use Excel to be my calculator. I'm just going to take that sample mean difference divided by the square root of the variance in that difference variable divided by my sample size. Remember, you could do it the other form too if you wanted to, if you found the standard deviation instead. But right, just, I just decided to do it this way, right? So notice that's a pretty low test statistic. So if I go to do this t.dist, right? Here's my test statistic, comma, here's my sample size -1 for my degrees of freedom, and then comma 1. Now this is going to give me the area to the left. I have a two-tailed test here, and my test statistic's positive. So I actually want the area to the right, and then I need to multiply it by 2. Right? So I first need to subtract that from 1, right? That, instead of giving me the area to the left, will give me the area to the right of my positive test statistic. I then say, well, it would have been equally as likely for me to see something on the other side. So I'll then multiply it by 2. Right? So I multiplied that by 2. I have an insanely high p-value. So really what we're thinking about here was, my alternative was that, is it not equal to, here, I'll put the symbol in here. So where is it? Here we go. Not equal to. So is it not equal to 0? So we assumed it was equal to 0. So I can reject, right, that the change, or sorry, I fail to reject that there's any change in the percent of people dying from COVID from this year to last year, which is wildly surprising to me. Right? We could do something different. We could do a one-tailed test. It's not going to really change. I mean, this test statistic is so low, even for a one-tailed test, right? P-value would still be 0.25. So even if I wanted to say, has the death percent or the percent of people who have died from COVID after contracting, has it went down? I could still reject that as well. And I can't say that there's any change here based off of this data. This is not a perfect, like, I'm not trying to make a statement about COVID. I just think it's interesting to kind of look into this. A better thing to do would be start to account for all these factors that vary across these counties. We would actually want to, control for the average income level in each county, right? Because that's going to tell us something about the vaccination side. We could control for the vaccination percent across counties. There's all these other things that we want to account for that then might actually lead to an opposite conclusion, which I'm going to try to actually keep using this data set. In the next couple of things that we're going to talk about, like next week, we'll start to look at Anova testing and eventually linear regression, right? And hopefully we can get a little bit better of a kind of attack on this type of a problem or question. but this is on its face kind of interesting. I was very surprised. I was getting this data, so I was like, I'm going to show them. Yeah, we've seen this huge decrease in the death percent, and then what actually ends up coming out of the data is it hasn't changed at all, which is relatively interesting. So I'll kind of show you that shortcut as well we could use here because it's going to be a little bit different. So if I instead use this, I don't think I had these in that complete file. I'll get those added in. So I can use that t.test, select my 2021 deaths, comma, go back up here. And actually, one thing you could always do is just type it into this formula. I only scroll up so that I can kind of show you. You can actually see it, and you can also see the little titles here. So the second variable was the 2020 death percent. So I select that column, comma. Now I have a two-tailed test, comma. I'm still using a matched pair example. So hopefully I get the exact same p-value that I did up here. Sure enough, I do. Okay. Any questions on any of that? Yeah, I actually have the, I do have the data on the percent vaccinated. So we'll build that in and actually start to look at, like, does that have any influence over death percentages, the number of deaths, and all these other things. So I think it'll be kind of interesting. I haven't really dove into the COVID data because I was exhausted for a very long time hearing about it, but now I'm at least kind of like, yeah, well, we kind of see what's going on, looking at the data. So the next thing, go over. So I'll introduce this idea and then I'll let us kind of get out of here. So this match pairs is like our first way of starting to try to control for other factors, right? We're looking within the same counties, right? We're looking within the same individuals. Okay? But there's a lot of other things that could be changing that we want to know, how does it impact the variable we're interested in, right? So the first thing that we're going to look at is kind of single factor Anova, right? So Anova stands for analysis of variance. And really all we're going to do is look for differences across different groups. So we kind of did this with two populations where we can compare one group to the other, but now we're going to actually be able to have like a continuum. So I could say something like, does the death percent from COVID vary across age brackets, right? Well, now I don't just have to say, does it vary, between old and young? I could say, does it vary between 0 to 10, 10 to 20, so on and so forth, right? So what we're going to think about here is, our null alternative hypothesis actually become, for these different groups, I'm going to assume they all have the same mean. So maybe I assume like that death rate from COVID is the same for every single age category group, right? So the mean from lowest category is the same as the mean from the highest category. The alternative is going to be, I'm trying to find, is there differences, right? Are they not equal to each other? Okay. So this is, I think, this is one of the things I steal from the book, because I actually really like this drawing, right? And I'll explain it in a second. So if the hypothesis is true, and that all the groups have the exact same mean, well, we still could see differences in their sample means, right? So let's assume that they all have exactly the same mean. We then go out and take a sample of people from 0 to 10, a sample of people from 10 to 20, so on and so forth, calculate the averages there. Well, it could be that we see sample means from different parts of the same distribution, right? If they all have the same mean, we still could see differences in their sample. Right? However, if those sample means start to become really far apart, right, instead of pretty close to each other, really far apart, what's probably more likely is that group 1 has a lower mean than group 4, right? And that there's actually several distributions going on. So it's kind of like what we did with two populations. It's just that now we're adding in several, right? We're adding in several populations here. Now the problem is going to become, I drew all these as though we had the same variance, right? They're the same height distribution, so they have the same variance here. What's going to be true in practice is, a lot of the times we're going to have different sample sizes across groups. They're going to have different standard deviations, right? The standard deviation of the variance that exists in the age category of 0 to 10 is going to be very different than the variance from 70 to 80 age category. but we can account for all this. Okay. So what we're eventually going to do with this Anova testing is we're going to take all these sample means across whatever groups we're interested in. We're then going to determine the variance of each one of those groups. Using the mean and the variance, we can actually come up with a test statistic, right? The problem is it's going to come from a new distribution. So I'm not going to make you guys use the F distribution in the sense that there is an F table. And it is wildly more complicated to use than the other tables we've looked at. I'm more so going to focus on all we really care about. So it's just a different type of distribution. So it looks something like this, if I can recall correctly. The F distribution is always going to have a long right tail. And how long that right tail is depends on the sample sizes you have across these groups and the variances that you have across these groups. So all we need to know is that basically I can come up with a critical value from this F distribution, and I can come up, and then I could basically plot my test statistic, which is now an F statistic, and I could determine my p-value here. And what ends up being true is for all of these differences across means, when it's across several groups, we're always going to be looking at just, is there a difference? And so we don't have to worry about tails because the F distribution is accounting for the fact that looking for differences across several groups, whatever measure I end up with is always going to be positive. So it's called analysis of variance. So, right, it's using the variance to come up with this test statistic. Well, variance is always positive, so we're always going to be just looking at the right side of the distribution. So we won't deal a lot with these critical values or F statistics. What we're primarily going to focus on is Excel output that gives us p-values, right? And then the approach is just like what we were doing before. We only reject the null if the p-value is less than 0. So the only time that we're going to reject that all these groups have the same mean is if we can get a low enough p-value, which then says, I'm rejecting that they have the same mean. I found strong evidence that the mean varies across these groups. So, yeah.
Okay, you said the p-value less than 0.
Did I say 0? I'm
I
sorry.
just wanted to clarify.
No, yeah. No, this is alpha.
Okay.
Yeah, sorry. Yeah, if the p-value is less than alpha, then we can reject. Sorry.
I just didn't know if it was.
Yeah. No, if I say something like that and I write something differently, let me know. It's been a long week, so. All right, so we'll pick back up with Anova testing. I'll probably put some more data files up there that we'll play around with some Anova testing in Excel on Monday. Other than that, have a good weekend, and I will see you guys on Monday.